states of matter, and atoms, elements, ions. Introduction: the puzzle pieces. If you want to build your puzzle, you need all the pieces. If you want to grasp higher chemistry topics, you need a working knowledge of the building blocks of life and the way they combine. Definition: substance. Stuff. It consists of physical, tangible matter. Solid. A state of matter. A state of matter where the substance in the questions has definite volume and definite shape. Again, solid. A state of matter where the substance when the substance in the question has a definite volume and definite shape. Liquid. A state of matter where the substance flows. It has a definite volume, but no definite shape. Gas, lowercase g. So solid was lowercase s, liquid is lowercase l, gas is lowercase g. A state of matter where the substance has no definite volume or shape. Physical property. These can be observed, seen, or measured or changed without altering the identity of the substance. Examples include melting point, boiling point, density, texture, color. Intensive physical property does not depend on the amount of matter present. For example, density, color, boiling point. Extensive physical property. The value changes depending on the amount of matter present. For example, mass and volume. Chemical properties. Chemical properties. A property that can be observed, seen, when a substance goes through a chemical reaction. Example includes toxicity, reactivity, flammability, chemical stability, physical change. The substance changes the state of matter, solid, liquid, gas. Chemical change. The substance combined with another substance or breaks down into something new. Physical versus chemical changes. One of the first things you will likely to be asked to do is to distinguish between, tell the difference, physical and chemical changes. There are plenty of the worksheets online you can use to the practice. The key question to ask yourself when trying to make that decision is, does the change alter the substance in some fundamental way? Can I get the original substance back easily without a chemical reaction? Example, if I rip a piece of paper in half, I've caused a physical change. I have not changed the paper itself. It's still paper. Even it is in the two pieces. If I burn the piece of paper, I've altered it in a way that cannot be undone. It's no longer paper. It's salt and ash. It's salt and ash. Element. The simplest type of the substance, made up of atoms with the same number of protons. We'll get to the subatomic particles momentarily. These can be found on the periodic table of the elements. The single most useful tool at your disposal. Compound is found when the two or more elements have been chemically combined and the new substance has its own chemical properties. For example, sodium chloride, table salt, NaCl. Mixture is formed when two or more substances are physically combined. Each part retains its chemical properties. Homogeneous mixture, uniform throughout. If you look at it as a sample from one part, it should look at and be the same as a sample from their different parts. Heterogeneous mixture, not uniform throughout. If you look at the sample from one part, it could be different than the sample from a different part. Source. Atomic theory. Matter, stuff, is composed of atoms. Mankind has moved up from Democritus' idea that matter is made up of tiny particles of smaller stuff until you can't break it down any further to John Dalton's theory, which gets a little more specific to the modern atomic theory. Statement of the Dalton theory. Elements are made of atoms. Elements are made of atoms. Atoms of the different elements have different mass. I'm sorry, I skipped the sentences. Atoms of the same element all have the same mass. So atoms of the same element all have the same mass. Atoms of different elements have different masses. Atoms combine in a ratio of the small whole numbers. You can't have half a sodium atom. Modern atomic theory. There are hundreds of thousands of papers on this topic, pages on the topic. So there are hundreds of thousands of pages on this topic, including the side trails into every scientist who made a significant contribution to the discovery of the atom. The models have come a long way. Currently, we believe atoms are protons and neutrons surrounded by electrons clouds. That's an overly simplified statement, but general chemistry courses rarely dive into the quantum theory right in the beginning. There will be a chapter dedicated to those concepts shortly. A general chemistry course is more likely to detail the history of the atom and the discoveries and the experiment that led to the knowledge of the subatomic particles. A short history of the atom, a who's who and what's what. Democritus coined the term atom. Technically, it was atomos, Greek for undivided. Aristotle, who had a more intellectual clout, rejected the idea, so it got buried for a few thousand years. That, ladies and gents, is an early lesson in the danger of being swayed by their popular ideas. Dalton came up with the first atomic theory. J.J. Thomson discovered the existence of electrons. Thomson's model, the plum pudding model, he basically said that the atom is a positive matrix with area of the electrons scattered throughout, like raisins in the plum pudding. Since the idea of plum pudding is foreign to the average American student, picture it like a chocolate chip cookie. The cookie part is a positive matrix and the chips are the negative part. It's a decent theory given that what Thomson knew at that time. It's long, but it was a decent start and challenged us to prove or disprove it. That's what the science is supposed to do. Incidentally, Thomson called these areas of negative charges corpuscles. I for one am grateful that creepy name didn't stick. The gold foiled experiment, the one that took out Thomson's model. The gold foiled experiment is one of the first ones chemistry teachers will gush about. It was run by Ernest Rutherford and two of his students, Hans Geiger and Ernest Marsden. They shot alpha particles, helium nuclei, which are small and positively charged, at the thin sheet of the gold foil, since the working theory of the day was Thomson plum pudding model. They expected all the particles to go straight through the gold foil. Most of the alpha particles indeed went through, but a few bounced at weird angles and some even bounced backward at the source. This led them to conclude that the area of positive charge was not spread throughout the atom as a plum pudding model suggested. But rather combined to a very small area of the atom. This is the nucleus. Let me say all that again, point by point. Who ran the gold foil experiment? Rutherford and two students. What did they do? Shot alpha particles at the thin sheet of the gold foil. What did they expect? Why? All the particles to go through because they thought the positive charge was spread throughout the atom. What happened? Most of the particles went through, but some bounced at a strange angle and some even bounced back at the source. Why was that surprising? If the plum pudding model was correct, there shouldn't have been any area of atom dense enough to stop the particles. What did they discover? The existence of the nucleus. Wow. Structure of the atom, yet more definitions. Protons, lowercase p, positively charged subatomic particles located in the nucleus. Neutrons, lowercase n, subatomic particles located in the nucleus that add mass to an atom but do not carry a charge. Electrons, lowercase e negatives, subatomic particles located outside the nucleus that does not add much mass, but does carry a negative charge. In a neutral atom, this will be the same number as the number of the protons. Atomic number, the number of protons in an atom. Positive charge. Mass number, the number of protons plus the number of the neutrons. Mass number equal proton number plus neutron number. Isotopes, atoms of the same element with a different mass due to the varying number of the neutrons. Two types of notation for isotopes. Hyphen notations shows only the element, name, or symbol. A hyphen and the mass number. For example, hydrogen-3. Nuclear symbol shows the element symbol with a left subscripted of the mass number and a left subatomic number. Example: what is the hyphen notation for nuclei with 13 protons and 11 neutrons? Step 2: solving the problem. 1. Look up the element with 13 protons, aluminum. 2. Add the number of neutrons and protons. 13 plus 11 equals to 23. 3. Write your answer in the hyphen notation. Aluminum-23. Tip: learn the following element names and symbols. It will make your life a whole lot easier if you can recognize certain elements by their names and symbols. Which elements and how many will vary by class. Here is a list I give my students at the beginning of the year. Note: it might differ for your class, but in my class, spelling counts, especially because I give them a periodic table with names spelled out of completely. Pay extra attention to spelling of beryllium, fluorine, phosphorus, nickel. Also be careful with the symbol Mg and Mn. I'm using the American spelling for phosphorus and sulfur. But if you are not in the United States, you might want to check which spelling you should use. Right. Brief introduction to the periodic table of elements, atomic mass, mass of an atom, measured in AMU, atomic mass units, which is approximately the number of protons and neutrons in an atom. Average atomic mass, a weighted average of naturally occurring isotopes of the atoms. Concept of the weighted average. I'm pretty sure I've just lost about half of you there with a definition of average atomic mass. Imagine you have a bag of mixed marbles. For simplicity, let's say there are only two sizes of marbles. You have a few bigger marbles and a lot of smaller marbles. The bigger marbles might have a greater mass, but their effect on the average will be smaller since there are less of them. Steps to solving average atomic mass problems. 1. Find percent as a decimal or change percent to decimal percent divided by 100. 2. Multiply decimal percentages by the respective weights. 3. Add the masses. 4. Adjust for proper sig fig if necessary. Example, if 13 marbles weigh 24.3 grams, 6 marbles weigh 30.9 grams, and 14 marbles weigh 21.2 grams. What is the average atomic mass? Step 1. 13 plus 6 plus 14 equals 33. 13 over 33 equals 0.3939. 6 over 33 equal 0.1818. 14 over 33 equal 0.4242. Step 2. 0.3939 multiplied by 24.3 gram plus 0.1818 multiplied by 30.9 gram plus 0.4242 multiplied by 21.2 grams equals. Step 3. 9.57177 gram plus 5.61762 gram plus 8.99304 gram equals 24.18243 grams. Step 4. 24.2 grams. Why is atomic mass not a whole number? It's a weighted average. See above. With that much multiplying, dividing, and adding going on, it's unlikely to be a whole number. What's the difference between the mass number and average atomic mass? Mass number is the mass of the particular isotope. You get it by adding the number of protons and the number of the neutrons. Atomic mass is a weighted average of the naturally occurring isotope of elements. What do you mean by naturally occurring? Technically, there could be a lot of isotopes for every element, but in reality, nature favors certain isotopes because of their stability. So, while it might be possible to get a carbon-6, meaning an isotope without any neutrons, it's very unlikely. There are 3 naturally occurring isotopes of the carbon: C12, C13, and C14. Quick periodic table orientation lesson. Group, family. A column of the periodic table of elements. There are 18 of these. Groups 1, 2, and 13 to 18 are considered main group elements. These are the ones we'll study in the greater detail to figure out reactivity. Sure. Notable groups with their special name. Group 1, alkali metals, except hydrogen. Group 2, alkaline earth metals. Group 17, halogens, very reactive. Group 18, noble gases, not very reactive. Period, series. A row of the periodic table of elements. There are 7 of these. Later you will see that they correspond to the energy levels. It will help you write electron configuration when the time comes. Metals, located on the left side of the periodic table. Note that hydrogen is placed above the first group, the alkaline metals, due to the way it reacts, not because it is itself a metal. Non-metals, located on the right side of the periodic table. Diatomic elements. When found in nature, they will always come in pairs. The prefix di means two. What are the diatomic elements? Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. How do I remember that? There are a few different memories hooks to. There are a few different memory hooks to help you memorize the diatomic elements. I prefer this. Start at number 7, nitrogen. Form a 7 across 2, oxygen and fluorine, and down 3, chlorine, bromine, and iodine, and add hydrogen, the 7th one. One of my colleagues uses honk brief. One of my colleagues uses honk brief. Hydrogen, oxygen, nitrogen, chloride, bromide, iodide, and fluorine. Because it sounds weird. Yes. It sounds like a huckleberry thing. Those are the symbols for hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. If it works for you, go with it. How can the periodic table tell us the ion charge of the elements? Valence electrons, outer shell electrons. These are the electrons. These are the electrons available to be gained, lost, or shared to obtain a stable configurations. Usually, this translates to 8 electrons in the outer shell. How many valence electrons do each of the main groups have? Group 1 equals 1 valence electron. Group 2 equals 2 valence electrons. Group 13 equals 3 valence electrons. Group 14, 4 valence electrons. Group 15, 5 valence electrons. Group 16, 6 valence electrons. Group 17, 7 valence electrons. Group 18, 8 valence electron, except for helium. That one only has 2 valence electrons. Octet rule, a guiding generalization that main group elements 1, 2, and 13 to 18 strive to get 8 electrons in their outer shells. Notable exception to the octet rule: hydrogen, helium, lithium, beryllium, boron. They are all content with less than 8 electrons in their outer shell. They are all content with less than 8 electrons in their outer shells. Electron dot diagram. Lewis dot structures for 4 elements. Write the elements symbol, and then write a dot to represent each of the electrons in the valence shell of an atom. I believe there is a formal way you are supposed to add them. Top right, bottom, left, top, then around again, right bottom, left top. I'm not that picky in the class as long as the student puts no more than 2 electrons per side. No more than 2 electrons per side, yeah. Ion. What an atom becomes when it gains or loses electrons. Also, a group of covalently bonded atoms with an overall net charge, but here we are referring to atoms that become ions. Cation, a positive ion formed when an atom loses one or more electrons. Anion, a negative ion formed when an atom gains one or more electrons. Why do atoms become ions? The key to this concept is stability. Group 18 elements, the noble gases, have a complete outer shell of the electron. For most of these, that means 8 electrons in the outer shell, but helium only has 2 electrons, so automatically those are in its balanced shell. The other elements really want to be like group 18 elements. They want a stable electron configuration. What kind of ion does each group form? Group 1 elements only have one valence electron, so they form positive 1 ion by losing that 1 electron. Group 2 elements have 2 valence electrons, so they form positive 2 ions by losing both of those electrons. Group 13 elements have 3 valence electrons, so they form positive 3 ions by losing all 3 of those electrons. Group 14 elements have 4 valence electrons, so they can form positive 4 or negative 4 ions. However, they tend to share electrons rather than give up or gain electrons. Group 15 elements have a 5 valence electrons, so they form negative 3 ion by gaining 3 electrons to complete their outer shell. Group 16 elements have 6 valence electrons, so they form negative 2 ions by gaining 2 electrons to complete their outer shell. Group 17 elements have 7 valence electrons, so they form negative 1 ion by gaining 1 electron to complete their outer shell.